Hello there, welcome to Boost Chemistry Revision. This is Ligaya and we're going to be going over rates of reaction, chemical kinetics. So the year 13 topic on rates of reaction today. Apologies for the slight delayed start. I've not been feeling well and I just had to get myself ready properly, as well as a few technical issues with the connection between the live stream and my screen share. So thank you very much if you're joining me live, and also if you're watching the replay, then welcome to you as well. So today's session, as we said, is going to be on rates. We're going to do a bit of revision of the key kind of things to remember, things to learn, how to calculate rates, how to calculate and work out orders, how to deduce the rate equation, calculate K with its units, and then we'll also be looking at the rate mechanism. Once we've looked at all the kind of theory and examples for that, we'll then look at the practice exam question to see how to put this theory into practice. So without further ado, I'm going to share my screen. Oh, and before I forget, if you are on here live, then please do write questions into the chat box so that I can answer any specific questions you have. Perhaps you want a clarification for something I've said or perhaps missed something, then please do just ask a clarification or ask a question in the chat and I'll do my best to answer your question. Okay, so I'm going to share my screen now. Okay, great. So as I said, this is rates of reaction. If you're on this live, I'm hoping that you're year 13 and you've already covered the stuff that you looked at in year 12 on the Boltzmann distribution and revising collision theory from what you learned at GCSE. So we're not going to be covering those things today. We're going to be looking at mainly how to build up towards the rate equation and calculating K. So come on. Okay, so the rate equation tells us how fast reactions are converted into products. And you probably know this is going to be a bit of revision from that year 12 stuff. So these four equations that I've written here, the first three are ones you probably learned in your year 12. Hang on a second, my pencil does not seem to be paired with my iPad. Okay, right, so these first three equations you're probably familiar with from year 12, calculating the progress of the reaction either by change in volume over change in time, change in mass over time, or change in color over time. We've got these different units based on the different measurements we might have been taking. So basically anything that's measuring how fast the reactants are being converted into products is measuring the progress of a reaction. So volume, mass, or color change are all measuring the progress of a reaction. At this, in this stage, when we're looking at the orders of reactions and going into the rate equation, we're going to be looking more at changes in concentration. So concentration changes you'll see when we've got reactions of solutions, whereas volumes will be normally we're calculating or measuring volumes of gases. Masses we're usually measuring solids, and changing color, that's when a precipitate is being formed or we've got some other kind of color change going on in a reaction. But changing concentration is the most common one that we'll be looking at in year 13, where you've got different solutions reacting and you're measuring the change in concentration to measure the progress of reaction. So just make a note of the different ways that you can calculate rate from that kind of data, as well as the relevant units based on what information you're using to calculate rate. So you may remember from before, but it may also be new to you, is that from the experimental information, in this case from a graph showing the volume of gas produced against time, you can calculate the gradient of the graph and that will give you the rate of reaction. And this is not just something we've plucked out of thin air. If you remember anything about calculating gradients, that's change in y over change in x. So in this example, y-axis is the volume of gas produced, so the change in y is the change in volume. And x is the time, so the change in x is the change in time over that same period of time that the volume changed. So calculating the gradient of this straight line is going to be exactly the same thing as calculating the change in volume over time. And therefore, this calculation that we've got down here, and we're just going to change the color so you can see what we're doing. So this calculation here is basically going to be exactly the same thing as this calculation here when it relates to the volume of gas produced divided by time. The only difference is that here in the graph, our time units are minutes, and up here we have our time units as seconds. So the only difference will be that the units are going to be centimeters cubed per minute instead of centimeters cubed per second. So some students do get quite confused about how to figure out what the units are going to be from a reaction, and they all just come from whatever information you've put into your calculation. So in this case, we had centimeters cubed on the top and we had minutes on the bottom, and that gives us centimeters cubed per minute. If we had mass on the top, seconds on the bottom, is going to give us grams per second. So always try to relate the units back to the things you're measuring. Okay, so it might seem simple enough calculating the gradient of a straight line graph like this, but you probably know that you don't always get straight lines in reactions. We often get curved lines that look like this. And again, this is still volume of gas being produced. We have a curve going up, so gas is being produced quite quickly to start with, and then it starts to slow down, then it levels off. So this is a classic kind of progress of a reaction graph that you would see. So you can't directly calculate the gradient of that curve. You could calculate the overall average rate, so how long it took to produce a whole set, a specific amount of gas. But it's more interesting and more appropriate and precise at A-level chemistry to be able to work out the rate at a particular point in time. Now, this is very common to do this at time equals 0, which would be the origin here. But the example that I've shown here is just time equals t, where t is just a time somewhere in the middle of that graph. So the key thing when you're trying to calculate the rate from a curved graph is you need to draw a tangent. Okay, and hopefully you know what a tangent is. It's a straight line drawn at the perpendicular to the normal at that point. The normal being a line that intersects the curve at a 90-degree angle. So we've got a straight line, this white line here that I've drawn. This is our tangent. This is our point, time equals t. The normal would be something like this, and our tangent is perpendicular to that normal. The main thing you need to think about when you're drawing a tangent is to place the ruler at that point and make sure that the line you're going to draw for your tangent doesn't cross the curve at any other point apart from time equals t. So once you've done that, you can do exactly the same thing as you did before, and you're calculating the change in y over the change in x. Okay, so just use delta to show change in there. So change in y over the change in x gives you the gradient at time equals t, and that equals the rate at time equals t. Okay, so we can calculate the rate of any reaction from the gradient of the graph that's showing the progress of reaction. So whatever you're measuring the progress in over time. Now this kind of links us nicely into, sorry, excuse me, I have a bit of a cold. This links us nicely into thinking about orders of a reaction. So orders of reaction link a specific reactant with how that specific reactant affects the rate of reaction. So in this case, our reactant is X. We've got the concentration of X on the y-axis in each of the three graphs on the top row there. And then we've got time on the x-axis. So these top graphs here are concentration time graphs. So what these are showing is that as the reaction progresses, we start with quite a lot of X. The concentration of X is high at the beginning, and in all of them, the concentration is going down. But in the first one, the concentration of X is going down in a straight line. So as you get less X, it's not affecting how quickly X is going down. So X is one of our reactants. If we have less of it and it changed the way that our reaction reacted, then we could say that it's affecting the rate. But if if the reduction in the concentration of X has no effect on the rate of reaction, we can say that that has zero order. Oops, that's supposed to be an underline. The zero order reactant is a reactant that has no effect on the rate of reaction. So in this case, we're showing the concentration of this reactant going down, but in another way you could think about it is if you double the reactant or change or increase it in any way, then you're not going to double or increase the rate. So a zero order reactant is a reaction that does take part in the reaction, but doesn't have a direct effect on the rate of reaction. So zero order is this one on the left-hand side, and we can look at it from a concentration time graph with a straight line going down, showing that as the concentration of the reactant decreases, as the reactant is being used up, there's no difference in how quickly it's being used up. Looking at the next one now, so this one here in the middle, as X is used up, the rate is slowing down. The gradient of that curve is getting more and more shallow. So what that's saying is the less X we have, the slower the rate. So X is affecting the rate. The concentration of X is affecting the rate. As the concentration of X is reducing, the rate of reaction is decreasing. And if this is happening proportionally, then we can say that reaction is first order. What this means is if you double the amount of X, then the rate will also double. It's a proportional relationship between that reactant and the rate of reaction. Looking at the third one then, for this one here, we've got a similar shape, but hopefully you can see that the gradient is much, much steeper at the beginning. Okay, so what we're seeing is that at the beginning of the reaction, a reduction in the concentration of X is having a much bigger effect on the change in rate of reaction. So the more the concentration of X decreases, the more the reaction slows. So we should be seeing a steeper gradient at the beginning and then much more of a slowdown towards the end. And this is what's called a second order reaction. And a second order reaction, if you double the concentration, then the rate will times by 2 squared, which is 4. So the rate will quadruple. And you can see these relationships more in the graphs at the bottom. So as we said, for a zero order reaction, we're now looking at the bottom graphs, which are concentration rate graphs. Oops. Or rate concentration graphs, I probably should write it as, because it's that way. Because rate is the y-axis. Okay, so what we're seeing here is at low concentration, the rate is a certain amount. At a high concentration, the rate is a certain amount. So no matter what the concentration of X, the rate is staying the same. We have a straight line, that's a straight flat line. So that's confirming what we explained earlier, that zero order reactants have no effect on the rate of reaction. We could double the concentration of X and the rate is not going to be affected at all because X in this situation is a zero order reactant. Looking at the middle one then, the first order one, as you can see, when the concentration is 0, the rate is 0. But then as let's say, if we count up the squares, let's say this is 4, then this becomes 4. If this is 8, draw a dotted line, then this becomes 8. Okay, so again, we're seeing a proportional relationship. As we double the concentration of X, we're doubling the rate. So we see a straight line, an X equals Y proportional straight line to show the relationship between the concentration of X and the rate, if the concentration of X, or if X is a first order reactant. And again, with a second order reaction, looking at the rate concentration graph, what we can see here is that we've got a curve now. So as you increase the concentration of X, just rub that out now. As we can increase the concentration of X, let's say this might be 4 here, and that one might be 8. Over here, it's no longer proportional. What you should find is that if you double the concentration, the rate will times by 4. If you triple the concentration, the rate will times by 9. So No, I'll write it like this. Okay, it's if x concentration of x doubles rate times by 2 squared, which is 4. And if the concentration of x triples the rate times by 2 cubed, sorry, that's the other way around, 3 squared, which is 9. So this will be times by 4, and this will times by 9. So the second order is basically the power at which you're going to multiply however much you multiply the concentration by. So if it was quadruple, then it would be 4 squared, which would be 16. Okay, so that's the relationship between second order. It's, rather than being a 1-to-1 ratio, it's a 1 to x squared ratio. Okay, so hopefully that gives you a good idea of what the meaning of orders of reaction are. But you're also going to be able to be expected in the exam to look at data like this from experiments and identify what the order of reaction is of different reactants in your reaction. So in this example, we've been given this reaction equation: nitrogen oxide and carbon monoxide and oxygen all react to make nitrogen dioxide and carbon dioxide. Okay, so these are all the reactants in our equation, but they all may affect the rate in different ways, and we can use the experimental data in the table to show that. So the important thing here is go systematically through each of the experiments and comparing which of the reactants changed and how those affected the rate. So if we compare experiment 1 with experiment 2, we can see that both the carbon monoxide and the oxygen stayed the same. So there was no change there, but this times by 3, the nitrogen monoxide. Okay, and what was the effect on the rate? You get your calculator out and just check 1.53 divided by 0.17. And that gives me 9, okay? And that means that 0.17 times 9 gives you 1.53. So we tripled the concentration of nitrogen monoxide, and we times the rate by 9, which tells us from what we were looking at just a minute ago that nitrogen monoxide is order 2, or the rate, the order with respect to nitrogen monoxide is 2. Okay, I'll change the color. Let's look at experiments 2 and 3 now. I'm just looking at it, and actually that's not making a lot of sense, because this is now going down, like decreasing by 3, and this is increasing by 2, so that's a little bit confusing. So instead of comparing experiments 2 and 3, we're going to compare experiments 1 and 3. Okay, because here the nitrogen monoxide is the same, so there's no change there, but the carbon monoxide has times by 2, and the oxygen has stayed the same. Okay, so only one thing has changed, that's the carbon monoxide. And if we look at the rate, there's been no change. So we've doubled the carbon monoxide concentration, but there's been no effect on the rate. And that means the carbon monoxide concentration is order 0. Or you can, in other words, you could say the order with respect to carbon monoxide is 0. Now we need to look at how we can identify the order of the oxygen in this equation. So I think, again, I'm going to compare, rather than comparing 3 and 4, because there's quite a lot of different changes between all of the 3 different reactants, I think I'm going to compare, just choosing a different color, 1 and 4. Okay, so 1 and 4 in purple. So here we've got that as doubling, that is staying the same, and that is doubling as well. And what have we got over here? 0.68 divided by 0.17 equals 4. Okay, so that's times by 4. Okay, so we already know that nitrogen monoxide was order 2. So if we doubled the nitrogen monoxide, we would expect the rate to quadruple, and that's what's happened. So that tells us that the doubling of the oxygen that we saw between experiments 1 and 4 did not have an effect on the rate. And that tells us that O2, you can't see this color very well, I'll change it to a different kind of purple. O2 is order 0 as well. Okay, so using these experimental data, we can compare experiments one at a time, so comparing one experiment with another directly and seeing how did the reactants change and how did the rate change, and this tells us how each reactant affected the rate. But as much as possible, you want to try and find experiments to compare where you're only changing one thing, but sometimes that's not quite possible, as we saw here when we compared 104. We had 2 different things changing, but hopefully by that point you have some information that you can use to already give you extra information to help you. So in this case, we already knew that NO was order 2, and so we could use that to eliminate that from the equation and then figure out that the O2 had no effect on the overall rate. Okay, so I'm just going to check if anyone has any questions. The O2 had no. Okay. No, so I can't see any questions. So we're going to go on to looking at how we can then use these order of reactions to calculate or to put together a rate equation, and how we can use that to calculate the rate constant K. So this is the rate equation here. Excuse me. Rate equals K, and then just remember the notation for concentration of, you should have seen there's probably an equilibrium and other parts of the course. So the square brackets means concentration of, in this case, A and B. So we've got the rate equals the rate constant K times by the concentration of A to the power of its order, and then the concentration of B to the power of its order. Okay, so if we just for example, take the information we just had over here, we've got, this is our overall equation, and these are our orders. If we apply that to the rate equation information we have over here, what we can say is the rate equals K to the power, times the concentration of NO squared, because the order of NO was squared, and then the concentration of CO to the power 0 and O2 to the power 0. Now you may remember that anything to the power 0 actually means 1, which means that this actually means K NO to the power 2 times 1 times by 1, which basically means we can ignore that, okay? Which means K rate equals K NO squared, and that is our rate equation. Because the other 2 reactants were order 0, they are not part of the rate equation. Okay, and we can do this for any reaction. We just need to find out what the order of each of the reactants are, and then put their orders into this structure of the rate equation. Once you have the rate equation, you're normally going to use the rate equation either to calculate the rate if you're given K, or to calculate K, the rate constant, if you're given the rate. So what we're going to do is we're going to take this rate equation that we've written out, and we're going to apply it to this example that we already looked at earlier. I'm going to just rub out all of these workings so that you can see a little bit more clearly. And so from this information, we have, for each experiment, we have data on the concentration of each of the reactants, as well as the rate of reaction. So we can use any line of each of these pieces of data to figure out the value of K. So we're just going to use experiment 1 as an example. So the rate is 0.17, and that equals K and then the concentration of NO is 2.0 times 10 to the minus 2 squared. Okay, and we want to find K, so we're going to rearrange this. K equals 0.17 divided by 2 times 10 to the minus 2 squared, and then that will give us K. Okay, and that gives me 425. Now you may be thinking, well, what are the units? And that's important. So if you have thought that, then well done. It's important to you have to calculate the units of K each time, because each time the rate equation is going to be different, and so each time the units are going to be different. So all we've got to do is plug the correct amount of units into the same equation. So you should have rate is going to be in moles per decimeter cubed per second. I'm going to just move all of this across actually, so it gives us a bit more space. So rate is in moles per decimeter cubed per second. And then, so that's basically our 0.17. And then we've got so concentration squared. So moles per decimeter cubed squared. Okay, so this, we're just, hopefully, you may have seen this in equilibrium. We're kind of putting the units into the equation. We could do it all together if you wanted to, but I think sometimes it's a bit cleaner to do it separately. So we've got rate and then concentration squared. So we have moles per decimeter cubed on the top and on the bottom. So we can cancel out one of those with one of these. So we can basically cancel out the that one. And then we're left with the second on the top and moles per decimeter cubed on the bottom. So the standard is to then bring the moles per decimeter cubed up by changing the power signs. So it would become mole minus 1 dm 3 seconds minus 1. And then again, the standard is to do the positive ones first. So we'd write dm cubed mole, so minus 1 second to the minus 1. And this would be our units. You probably wouldn't be marked wrong if you did this one instead, but just know that it's a standard convention to do the second one there. So when you're using experimental data to calculate K, you need to both calculate the value and calculate the units. Okay, has anyone got any questions so far? Okay, so the last thing we're going to go through before we go on to a practice question is looking at how to work out what the rate determining step is. And again, the rate determining step is all to do with the rate equation. So hopefully I still have that in my paste. Yeah. So we worked out from our experimental data the orders of our reactants, and that gave us the rate equation, which we have here, rate equals K, and then times concentration of NO squared. So the rate determining step is the idea that this reaction, okay, that is our overall reaction. That's the reactants in our reaction and the products in our reaction. But the rate equation has told us that carbon monoxide and oxygen do not take part in the rate determining step. They are not affecting the rate. So this reaction must happen in more than one step. And it's only nitrogen monoxide that is present in the step that affects the rate. And that's what we call the rate determining step. So the only reactants that are in the rate determining step are the reactants that are in the rate equation. Okay, so that's why the rate equation is so important. And then in the same way as when we wrote the rate equation, we put the number of well, I guess we didn't, that's not quite how we did it. So right, I'll take that back. This is probably, if you remember in equilibrium, the way we did the equilibrium constant, and we used the moles from the equation to put as a power in the equilibrium constant. That's kind of what this is like here, is that what we're saying in this rate equation here is that the rate determining step has 2 moles of NO in it. So in order to write the reaction equation, we're going to say 2 moles of NO, and then we're going to say that's equal to something, possibly 2 things. Yeah. And then the other part of the equation is going to have the CO and O2, and probably something that was created in the previous step. And then we're going to hopefully create NO2 and CO2 by the end of that equation. And I'm just thinking, okay, well, I think what we're going to do is have just one product there. So when you're actually writing the rate determining step, the important thing is just to make sure you've got the right number of moles of the reactants that are in your rate equation, so as we have in this left-hand side here. But you may need to kind of work out some sort of feasible intermediate that would have been produced in that reaction to then react in the second step. So I'm going to suggest perhaps we've created N2O2, but you know, it wouldn't be wrong to suggest maybe N2 plus O2 or something like that. Anything that sort of makes sense that could have been formed from 2NO. So I'm going to go with this version that I've written over here, but I'm going to leave that over there as an option. And if you create N2O2, but it's not a product in the overall reaction, then you're going to react again in the second step, so that in the same way, you may remember doing this from free radical substitution. In propagation reactions, a new radical is produced that's reused again. In this case, we've got an intermediate produced that's reused straight away. So overall, it has no effect on the reaction. But when you put the two reactions together, the intermediate cancels out. We have all the products on the left-hand side and all the all the reactants on the left-hand side and all the products on the right-hand side. And hopefully this should all balance as well. Let me just double check. I think I may not have got the correct balancing from in the equation, actually, now that I think about it. Yeah, if we look at that top equation, I just I didn't copy it correctly, but it should have been 2, 1, 2. Oh no, that is balanced. That is enough. Okay, so N2O2. See, my problem at the moment is we've got too many N2s here and just one NO2 here being produced. So perhaps what we need to do is have something produced that okay, well, I guess I didn't think this one through. Sorry about that. It's important that both reactions balance, but it's also important that we have 2 moles of this because that's in the equation. So even though we only have 1 in the overall equation, I think that means we need to create something over here extra that somehow absorbs that extra NO. Okay, you know what I might do is I might give you a different suggestion, a different suggestion. So for the rate determining step, we're going to use a different example of an overall equation. Sorry, I didn't think that one through. We're going to use the same rate equation. Sorry, same rate equation. Okay, and the same start of our rate determining step, because that's the most important thing. But instead of our overall bit equation being that with the CO and O2, we're going to use a different example, which is 2NO plus O2 makes 2NO2. So okay, so that's our overall equation, where the rate equation is the same as what we had before, just the two NOs are taking part in the rate equation, which means that the O2 must only be part of the non-rate determining step. So in the first step, we could produce in the first step, we could produce the N2O2 that I suggested, and then react it away. So making sure that it gets reacted and it's not remaining there at the end. If that reacts with O2, we can then produce 2NO2. So if we put those two equations together, the N and 2 O2s will cancel out. We have our 2NO and O2 on the left-hand side and our 2NO2 on the right-hand side. And that's basically how you work out the rate determining step. Apologies for that previous example. Hopefully this one is a bit clearer. If I work out how to do the next one, the previous one, I'll let you know. But it's just a little bit harder to do that right now as we are live. I was needing to work out something that I think my sick brain is not allowing me to do. Okay, so we've gone through all the kind of theory stuff now, and we're just going to spend a few minutes now looking at a practice question. So this is from the OCRA paper 1 in 2018. And we can see we've got information, the questions about rates. We have aqueous ions reacting with aqueous iodide ions, and we've been given the overall equation there. The student carries out 3 experiments to investigate how different concentrations of Fe3+ and I- affect the initial rate of the reaction, and the results are shown in the table. This is a similar type of table to the one we had in the example, and it wants us to determine the rate constant, which is K, and a possible 2-step mechanism for the reaction that are consistent with the results. Okay, so determining the rate constant is we're going to be asked to calculate. We want to figure out the rate equation and then use the rate equation to calculate the value and units for the rate constant, and then use the rate equation to figure out a 2-step mechanism for this reaction. Okay, so comparing experiments 1 and 2, Fe3+ doubles. This doesn't change. And this looks to me like it doubles as well. Okay, so the order with respect to Fe3+ is 1. Or you could say Fe3+ has an order of 1. Okay, comparing experiments 1 and 3, because it looks to me like 2 and 3 have too many things changing. The Fe3+ doesn't change. This times is by 2. And this to me looks like it times is by 4. I'm going to double check with my calculator. Yeah, 3.8.1 times 10 to the minus 4 times 4 is 3.24 times 10 to the minus 3. Okay, so when we doubled I minus, the initial rate quadrupled. So the order with respect to I minus is 2. Okay. That gives us the rate equals K Fe3 plus, and then I minus squared. Okay, so we don't really need the 1 here. I just wrote it in to make it clear, but because something to the power 1 is the same as itself, we don't really need that there. Okay, so now we want to calculate the value of K. So we need to just choose any of the experiments and just substitute the data in. So let's look at experiment 1. The rate is 8.1 times 10 to the minus 4. And then the concentration of Fe is 4 times 10 to the minus 2. And then I minus is 3 times 10 to the minus 2, but we want to square that. Okay, and then we want to just rearrange for K. And just copy this stuff. Paste it there. Okay. Okay, so we put that into our calculator to find K. And I get 22, K equals 22.5. That's what my calculations get. I'm going to just double check this with the mark scheme. Yeah, that looks good. And then we want to also calculate the units. So we have the rate on the top, moles per decimeter cubed per second. And on the bottom, we have moles per decimeter cubed, and we have it 3 times, so cubed. We can cancel one of those with that, making that 2. And then that means we have moles minus 2 dm to the 6 s minus 1, which we're going to write in this order instead. Okay, yeah, so that's our K with our units worked out. We'll put it that there so it's kind of all together. K equals 22.5 decimeters to the 6, moles to the minus 2, seconds to the minus 1. And then now I think we've got some additional answer space. Great. Now we want the 2-step mechanism for the reaction. So the first step, or the slow step, is going to be the step that involves just the things that are in the rate equation. So we have 1 mole of Fe3 plus and 2 moles of I minus. Okay, so it's going to be our slow step, or our first step. So we can see that compared to the first, the equation that was given to us, the overall equation here, you used up the 2 I minuses, but we've got 1 extra Fe3 plus left over. So that's going to be in the second step. Okay, and we're going to produce 2 Fe2 plus and I2. Okay, so we've got to work out how we're going to produce that from the 2 steps. So we want to just work out what's possible to produce from the slow step, Fe3 plus 2 I minus. One possible suggestion could be FeI2 plus. So you just kind of put them together and show what the overall charge would be. Or perhaps we've got 1 Fe2 plus and I2 minus. So they've created a molecule perhaps with something there, or Fe plus I2. The idea is that there could be all sorts of different feasible possibilities. What you write down just has to be feasible from the information you're given. So I think we're going to suggest FeI2 plus. So all I've done is put Fe and the two I's together as if we're making an ionic compound. We've not got enough minus charges to balance out the 3+ charge, and that's why we're remaining with an ion with a positive charge there. Okay. But then anyway, it doesn't really matter what you've chosen there, because then that's going to be reacted away in the second stage here. And if we react Fe3+ with FeI2+, then that gives us our products from the equation. So 2Fe2+ plus I2. I haven't actually drawn the state symbols in, but I think you should draw the state symbols in because they were given to you in the original equation. So it is important to put them in. They're probably not going to be specific marking points for the state symbols, but they may not give you the full marks if you don't include them. So the key thing is that this intermediate could really be anything as long as it's feasibly produced from these first two reactants. But the most important thing is that when you add together these two reactants, you get 2Fe3+, and when you add together that, you get 2I-. We cancelled out the FeI2+, and then we get 2Fe2+ and I2. So this, adding the two mechanism steps together gives you the overall equation, and that's what's really important. Beyond obviously the slow step, the rate determining step being produced from the rate equation. So have a go at this one yourself, and feel free to use the mark scheme to double check exactly what marks are given for that. And I hope this has given you a good review of chemical kinetics. I'm going to stop the share there. So thank you again if you joined me live. Thank you if you're watching a replay of this. I realise for some of you perhaps it's a bit late at night. Please do join us again on, let me double check what the schedule is. I believe that Dr. Owusu will be doing a session on the weekend on Sunday. On Sunday he's going to be doing a session on redox titrations. So if you've already started looking at redox titrations, then that would be a really good one to join into. He'll go over kind of revising redox stuff that you need to know from before, half equations and balancing with full ionic equation, as well as looking at the experiments, the redox titrations and what you need to know for that. So definitely make sure that you join in Sunday's session. Look out for post on Instagram or an email reminder that will give you the link for that. Something else to note is that we've just been moving to a different platform for our chemistry clinic. So if you're already a member of the chemistry clinic, then you'll be receiving some new login details to log into the new platform for that anytime soon. So look out for that too. Thank you again for joining, and I'll see you again soon.